Good afternoon. Hello. My first slide. 51 years ago, I graduated from Georgia Tech in physics. That was the last year of the Apollo landing program. So 51 years later, now we have Artemis, thank goodness. And I look forward to watching all of you, the future generations, lead us forward with that program to the moon. Don't skip past the moon and go to Mars. First do the moon, lots to be done there. One of the things one can do is to use the moon as an occulter to look at the solar corona and to look at other things. You may be a Red Sox fan from Boston or a White Sox fan from Chicago, but everybody is going to hit a home run on the moon if you're with the LunaSOX team. So remember that. Says next. Okay, so this is an instance where I was able to actually publish a paper before I gave a talk. Maybe that's the first time in 50 years that I have done that. So all the details of this talk are in this paper. If you Google Frontiers LunaSOX, you will immediately find a free access version of that paper. I would like to thank in particular Shadia Habal of the University of Hawaii, Manoa, who's a long-term solar eclipse observer from the ground on Earth and was very interested in this concept of doing the same thing from the moon and doing it much more often. So we published a paper back in 2013 there, and a white paper was submitted for the Heliophysics Decadal Survey, which I guess comes out like next year or something. So we'll see how that goes. Let's see. Okay. Okay, so this is a beautiful example of the Great American Eclipse of 2017 that I saw myself from South Carolina, but more scientifically, Shadia and her colleagues watched this from their vantage points. And this is a multispectral image. So of course you see the sun fully occulted by the moon in the center here, which is the best way to see the solar corona, is using the moon as the occulter, which I will tell you. And we have different colors here. In the white, we have the wideband visible spectrum. In the green, we have the iron 14 line, which you can see is quite common in some of these coronal streamer type structures. And then the open field lines are actually not low altitude in red, but they're going from low to high altitude, as you can see around the poles. And so this is a way of understanding the thermophysical environment of the solar corona. In this instance, from a few tenths of a solar radius out to about 4 solar radii with this kind of imaging. And that is limited by the fact that you're looking up through the sky at totality during a solar eclipse. So that is about 1/billionth of a solar brightness. But if you could do better than that, you could see further out. Next, please. So what's the problem? Oops. Let's go back. Sorry, I hit the wrong key. Go back one, please. Okay, so one of the problems we have these days is we lost a satellite. So here's the sun, and you can see an image of the sun. It's the solar disk and the coronal photospheric, chromospheric type stuff above it. There's sort of a dark region here because we do not have a multispectral coronagraph that images in the inner corona region here, the dark region, and then it starts out. Here we have SOHO, C2 and C3 and other instruments which have somewhat limited resolution, as you can see. They are very good for looking at CMEs and things like that, but they are limited in their ability to look at very small scale features. We would like to understand things like the difference between the solar wind flow at low beta, which means temperature over magnetic field, so high magnetic field. And as we go to high beta, what is happening, and that is this sort of transition region here, which these particular authors, West et al., have called the middle corona. So how can we fill this gap in, which we currently have without solar SOHO LASCO C1? Next, please. So this is a way. So you put yourself in lunar orbit, and with the telescope that looks at the sun, but you don't want to look at the sun, of course. So you want the sun to be below the local horizon, looking at the lunar limb. So let's say we're looking at this from behind the moon, anti-sunward toward the sun. We're looking over an edge here, which has topography of about plus or minus 8 kilometers. And you can see that down here, of course, to some extent here. But what you can also see is a very sharp edge. There is hardly any diffraction here. And if you watch the Earth rise or set here, and if you calculate it, if you're looking at it from maybe about 10 lunar radii behind the moon, anti-sunward, the diffraction region is about 7 meters at the lunar limb. Okay, let's see. So it is a very sharply defined edge to be looking at something, for example, at the solar corona or some other object. Next, please. So here's the log of solar brightness here. So the sun itself is way up here at the top. The blue sky of today, we're looking at today, is about 1 millionth. And as I said earlier, here's 1 billionth for looking at totality during a total solar eclipse. And if we're looking from the environment of the moon, literature tells me in terms of scattered light from dust around the moon that we're down around here, around 1 trillionth of a solar brightness. And you can see that's actually the range of SOHO C1 to C2 to C3. So we can actually do heliospheric imaging, to tens of solar radii out here, as well as looking at the details of the corona, and we can look quite close to the solar disk at low solar altitude in this way. We'll be able to do this. It depends on the kind of orbit we have for the orbiter. So if we're talking about an elliptical orbit, 1 by 10 lunar radii, we're talking about getting an eclipse every 12 hours or so on average. If we're in a low altitude orbit, it's 1 hour. If we're sitting on the surface of the moon, of course, looking at sunrise or sunset, it's every 2 weeks. But that's a lot more often than every year or two when we get a solar eclipse to look at from the ground. Of course, the brightness resolution would be much better here. Next, please. So this is just a cartoon. So we got the sun sitting over here, the moon sitting over here. So P1 is, for example, the Artemis P1 satellite. Artemis P1 and P2 are currently in orbit around the moon. So if P1 is sitting here, this is the geometry that says that
1 minute.
Okay, I'll have to move along. That you can see, the solar corona from the edge of the solar disk, and as you move a bit closer in here, you see it starting from further out. So wherever you are on this line kind of tells you the minimum coronal altitude you can look at. Next, please. This is just I won't go into detail. Each red point is like a 2-minute sample of the position of the Artemis P1 spacecraft. And that tells you, for example, at this particular point, that I can see things above 4 solar radii. Down here, I can see something above 1 solar radii. And it's varying in time as the orbit processes around the moon. And so if you have more control of the orbit, you can pick times where you get a much higher density of eclipses to do your observations. Next, please. Next, please. So in summary, what we're talking about here is doing heliophysics from, by, and of the moon. From the moon, obviously, with Artemis, by the moon using the lunar eclipse. And we can do lunar science, such as the solar dust and gas atmosphere, with the same kind of measurement. We can do it at very, very high cadence, high resolution, and high sensitivity. And we can do it in different ways depending on what kind of orbit we have, and we can control the orbit to move it for that respect. The bigger picture, for Artemis, the Artemis program is a lunar space weather network that we could conceive of. And also we need communications relay, for example, for things on the far side of the moon. So a network of satellites that does this sort of thing, as well as communications relay, would be terrific. And again, Google Frontiers LunaSOX for free access to the paper. Thank you very much.